Welcome. In this episode, we are still continuing our bob in uniform motion. That's because there's a lot of things to talk about. Now, you will see some equations and some graphs which are familiar to you. This is the equation of the same motion that we saw before. That's right, we're still talking about the same thing. If you have not seen this before in the previous episodes, I strongly advise you to pause right now, go back, visit those episodes, and then come over here. This is a continuation, okay? If you don't know about what happened before, you're not gonna follow. Okay, anyways, so whatever we saw before, we're gonna do the same thing. We have the same equation here. Now, you can see another equation which I haven't written before. And I wrote it right now because we have introduced the two kinds of velocities, the average and the instantaneous. So we can make sense of this equation now in general. You see, 1 was the initial position of the bob. You see, at time t equal to 0, it was 1, and that is at 1. So in general, I can just call it as x0, and x0 represents the position at time t equal to 0. And this 2, which is coming along with t, is the velocity. Now you may ask, well, which kind of velocity? Is it average value or is it the instantaneous value? And I would say it doesn't matter because bob is still in uniform motion. Remember, characteristic feature of uniform motion, average value, instantaneous value, same thing. At any instant of time, any interval of time, same thing. And also, I showed you, this is the same graph which we drew before. We saw that in xt graph of any uniform motion looks like this. It's a horizontal, it's a straight line. It's not horizontal, it's a straight line. And I've drawn the same thing here. And for some reason, I redrew it over here. I drew it once and then I thought, okay, this is too small, and then I redrew the whole thing over here. Okay, the lines may look a little bit skewed. I think I did not get the angle right here, but whatever it is, this represents the same thing as before. So the question today we are going to ask in this episode is, can you calculate the velocity? It doesn't matter which velocity, it's the average and the instantaneous is the same thing because we're in uniform motion. And in general, by the way, in general, when someone says velocity, he or she actually means instantaneous velocity, okay? We're going to be using that as our standard. Anytime someone says velocity, it always means an instant velocity. Anywho, alright, so can you calculate the velocity just from the xt graph? The question is basically, see, we just saw, I told you that, equation contains all the information about the initial position, it contains the information about the velocity, and the graphs must also contain the same information because these two are the same things. So now the question is, if I don't give you this, and if I just give you the graph, can you calculate what the velocity is? There must be some way to do that because the graph must contain the information. How are we going to do that? I'm going to tell you how, and I'm going to concentrate on this graph. It's big and nice, okay? Alright, I'll tell you what we need to do. All we have to do is draw a right-angled triangle somewhere, taking this straight line as the hypotenuse. You can do it wherever you want. I will do it wherever there are already markings available. So what I will do is I'll draw a right-angled triangle this way. Here, like so. And I'll call this angle as alpha. Okay, now you can draw this right angle triangle however small you want, however big you want, it doesn't matter, you'll end up with the same answer. Okay, now let's concentrate on this length. What is this length? I'll call this as the vertical length, and the vertical length, as you can see, it is 9 minus 5. It's this distance. That is 4, that's 4 meters. Okay, and what is this horizontal length? Well, horizontal length is 4 minus 2. You see, it's this one. It is 4 minus 2. That is 2 meters. That's 2 seconds. Sorry, that's 2 seconds. Do you know what this represents? This represents the displacement of bob. Remember, bob is moving this way. Bob is not moving this way. He's moving this way. You remember that, right? I did that intuitive graph for you. Yeah, here it was. Good thing I found it over here. Remember, bob is moving this way. Bob is not moving like so. It's not doing that. It's just snapshots. Anyways, so this represents the displacement, and this represents the time interval. What more do we want? We can just look at the graph and we just divide the two guys and we get the velocity, 2 meters per second. Done? Let's go home? No. let's not go home, because I want to take a moment over here. Actually, I want to take the time to explain to you some general property of a graph. Okay, this is an amazing thing about a graph. Let's explore this in a little bit detail. First thing, if you know trigonometry, now if you don't know, don't worry. I'm just telling you as an FYI, if you know trigonometry or you remember your trigonometry, then you may remember that this is the opposite side, this is the adjacent side. So this ratio actually represents the tan ratio. Okay, it's tan alpha will give you the same answer, 2 meters per second. Now if you don't know trigonometry, it's okay, it doesn't matter. The only thing you need to remember is just by looking at alpha, you can figure out what this ratio is. It can be done. Okay, you need trigonometry for that, but it can be done. And that's why, regardless of which triangle you take, for example, even if I take a triangle here, over here, I would get the same alpha, right? The angle is the same. And so if I take the vertical divided by the horizontal, I would end up with the same answer, 2 meters per second. Obviously, because it's going in a uniform motion. So you take it anywhere you want, you get 2 meters per second. And the instant velocity is also 2 meters per second. We don't have to do it again. However, I'm going to tell you what this is called. This ratio, in general, we give it a name. We call that as the slope of the straight line. Allow me to explain what slope is. To understand what slope is, I want you to imagine that there's some dude over here standing and he wants to climb this, let's call this as a mountain. Okay, his friend Bob is here or something, whatever that is. Okay, for now, just forget about these guys. Just forget that this is X and this is T. Just imagine that, you know, Bob is moving along this particular mountain. Now, in order for Bob to move this way, you can imagine that Bob does two things. As Bob is climbing, he moves forward along the horizontal and simultaneously he moves vertically upwards. You see that? When he comes from here to here, you can imagine he actually moves this way and he moves this way. Similarly, when he goes from here to here, he moves horizontally and he also moves vertically. Now, what does slope represent? The slope represents how much vertical climb he needs to make for every horizontal step he takes. Let me write that down. So, the answer for this is yes, by the way, obviously. But let me write what slope is, okay? We define slope as the ratio of the vertical climb. So here is the vertical climb divided by the horizontal step. So for every horizontal step, how much vertical he has to climb, we call that as the slope. In our example, that number turned out to be 2. It's 2 meters per second, but I told you, forget about meters per second for now. Just imagine this was a mountain. If this is a mountain, what does this 2 represent? The 2 represents that for every horizontal step, I just call it as head step, he has to move 2 steps vertically upward. Climb 2 steps up. That's what the slope tells you. The slope tells you this ratio, vertical climb divided by the horizontal step you move forward. And this is an interesting thing about a graph. And the reason for this is slope is very intuitive. Think about it. What if this mountain had a slope of 3? Can you imagine what the mountain would look like? If the mountain had a slope of 3, then for every 1 step he moves forward, instead of moving 2 steps up, he would have to move 3 steps up. You see, that's the meaning of slope equal to 3, right? 3 vertical climb per horizontal step. So in that case, the dude would end up in that mountain. If he was climbing, he would end up not here, but he would end up somewhere over here. Okay, so can you imagine that mountain would be somewhat like this? It would be steeper, it would be more sloping. That's why we call this as a slope. Okay, it is more sloping this way. In fact, I can have it over here. Look at this. If there was another mountain this way, this Bob, okay, you can think of it as twin brother or something, but you consider this Bob, you can see this particular Bob is more sloping, because for every horizontal step someone takes over here, he has to take more vertical step. It's harder, it's steeper to climb. That's the whole idea behind slope. That's why we love graphs. And guess what? Just by looking at the slope, you can calculate what the velocity is. So that's the answer for this. The slope of xt gives velocity. Is it average velocity? Is it instantaneous velocity? Remember, uniform motion, guys. Same thing, same thing. What if it's not uniform? We'll talk about that some other time. For now, let's concentrate on the important thing. I want you guys to remember this forever. The slope under xt graph always tells you what velocity is, and I don't want you to just mug it up. I want you to feel this. Think about it. Slope is always the vertical divided by the horizontal. Vertical is meters, horizontal is seconds, so meters per second, well, velocity, okay? This now allows us to do some qualitative analysis on graphs. Let's quickly do that and end this episode this way. So what I'm going to do is the following. Imagine an xt graph, and you can see I have not put any markings because I really don't care about numbers. I just want to get a qualitative feeling. So here is Bob, okay? And let me introduce one more character in our episode, and that character is going to be Marley. Okay, this is Marley. Alright, now both Bob and Marley are moving, but can you understand the difference between the motion of Bob and the motion of Marley? Without numbers, just a feeling for it. Think about the slope. Quick question, who has more slope, Bob or Marley? Well, I just showed you. Slope is how steep a graph is, alright? Marley's graph is much steeper compared to Bob's graph, and therefore you can clearly see Marley has more slope compared to Bob, so Marley is moving much faster because its velocity is more compared to Bob's velocity. In fact, you can pretty much see what's going on over here. In fact, t is equal to 0 is somewhere over here, okay? So Marley was actually quite behind over here, and at this moment in time, Bob had already progressed. Bob was already somewhere over here. But then as time progresses, you can see Marley starts moving faster and faster and faster and faster and faster. And at this point, at this moment in time, Marley overtakes Bob. And then Marley says bye-bye. And Marley goes faster and faster and faster. You see why we love graphs? Because of this. We can just look at it and qualitatively analyze this. Of course, using equations we can do that as well, but sometimes you just want to step back and just look at things qualitatively. Let me introduce one more character. Let me get rid of Marley now. Let me introduce one more character. Let me consider Sheila, and Sheila is doing this. Okay, so let me redo Bob. Bob is doing this, Bob is doing this, and Sheila is doing this. I want you to pause for a moment and tell me what's going on. What is Bob doing and what is Sheila doing? Can you imagine their motions? Okay, if you have answered, let's see whether your answer is right or wrong. If you haven't answered, it doesn't matter. I'm gonna tell you anyways. So, what is Bob doing? Well, Bob is doing something usual. At time t equal to 0, he's over here and then he's moving slowly this way. But look at Sheila. Sheila is not doing that. Sheila at time t equal to 0 was here. She was already at a high value of position. And then as time progresses, she's actually moving along the negative direction. If you thought of a dude over here, this mountain is sloping downwards. We call this as the negative slope. In fact, Sheila's velocity is negative. The minus sign is just telling you that she's moving in the opposite direction of our chosen positive. Remember, we chose this as our positive x. Sheila is moving in the opposite direction, and so her velocity gets a negative sign. So velocity is sign sensitive. Don't worry too much about this. We're gonna talk about all this in great detail. We're gonna do some practice problems and all the fun stuff is going to happen, but just try to understand this qualitatively, okay? Now here's my question. If you look at Sheila's velocity and Bob's velocity, which is bigger? Can you think about that? Which velocity is bigger? Now Sheila's velocity is negative, but that negative sign, don't think of that negative sign as a number which is smaller than a positive number. The negative sign is only there to represent the opposite direction, okay? But I want you to look at the magnitude of the slope. So this mountain, Bob's mountain, is sloping upwards, but can you see the alpha for Bob is not that great. This is the alpha. The alpha for Bob is small, but if you consider the alpha for Sheila, look at this alpha. ooh, this alpha is more. So although Sheila is moving in the opposite direction, you can also understand that Sheila is moving with a much faster velocity, much higher velocity compared to Bob. And I have one last character for you which you can tell me what he's doing. So let me get rid of Sheila, let me get rid of Bob, and I have one last character, and that is George. And George is doing this. Okay? Pause for a moment and tell me, what is the slope of George? You have to tell me this. Imagine a dude. The slope is how much vertical climb someone has to get for every horizontal step. Well, guess what? This dude is not getting any vertical climb. There is no vertical climb. There is no slope. If you think of this as a mountain, then the mountain is not sloping up, nor is it sloping down. Therefore, the slope is 0. If the slope is 0, then the velocity of George is also 0. Ooh, this makes perfect sense, because the graph is identical to what we had when Bob was at rest. Everything makes sense. I love this. So, the short summary is the slope of an xt graph represents velocity, and slope represents the vertical climb divided by the horizontal step. I will see you in my next episode. Stay tuned.